Cara is going to be speaking to us about a more technical aspect of uncertainty and risk management. And Cara, you're going to have to tell us what DFN actually is before we even start. But everyone, please put your hands together for the fabulous Cara Gupta. Thank you very much.
Thank you. And I'll just check that that's sharing all right, Sarah.
Yeah, all
Okay,
good.
amazing. So thank you, Sarah, for the very kind introduction. And good morning, everyone, and to anyone that watches this at a later point in time. But as Sarah mentioned, I'll be speaking to you today about using DFN modeling to reduce structural uncertainty in mining operations. So I'll start by giving you a very brief background and introduction to me and who's giving you this presentation today, followed by some of those structural uncertainties that we encounter, what a discrete fracture network model is, what are the inputs to these models. I'll give you some application examples from the mining world, and then I'll leave you with some final thoughts. So as Sarah mentioned, my background's in geology, which I studied in Ireland. And following my graduation, I joined WSP here in London in their mine engineering and stability team. And over the past year and a half, I've done a range of different things with our projects, including geotechnical QA/QC of core, different stability analyses, a lot of structural geology analysis, and of course, discrete fracture network modeling. So before I jump into the weeds of the presentation, to give you some context to this acronym that I keep repeating, DFN stands for discrete fracture network. And when we talk about a fracture, it's this general term for any separation or discontinuity in a rock formation. And this can come in a range of sizes. So fracture can be referring to things like faults, joints, open or broken veins or foliation. And when we talk in the context of a fracture network, these networks have a big influence on how the rock mass behaves and therefore its stability. And that's why we like to define and generate them for future planning and mine optimization. So, what are some of these structural uncertainties that we encounter? The first one is in relation to data availability, which is normally limited and variable based on what's available from the mine itself. And the data that's collected, there tends to be a focus on those smaller or large scale structures. And this is because those intermediate or inter-ramp structures in an open pit tend to be more challenging to capture or require a lot more effort. So there is that gap in the scale of structures collected. Another uncertainty is in relation to geological complexity. We can have really complex heterogeneous rock masses with multiple fracture sets, variable persistence, and have spatial variability involved. And as a result of some of the models or analysis that we do, it can result in a non-unique interpretation. Another uncertainty is the consideration of new data. So conditions change as mining evolves and there's further development. And this also comes with new data becoming available. And these models need to be able to adapt. And this is why a living model approach can be more beneficial. As one of the presenters started their talk with yesterday, we make decisions under uncertainty. And this is not a complete list. This is only a few uncertainties in relation to structural data that we come across. And today I'm hoping to show you how a DFN model can reduce these uncertainties in order to allow us greater reliability in our predictions and decision making. So, what is a DFN model? Well, a DFN model seeks to represent a rock mass structure stochastically using field data of the in situ fracture network. So what this means is a DFN generates these fractures randomly, but they're based on the statistical definition of the in situ fracture network. And we can do this by defining three key parameters of that fracture network. And those parameters are fracture orientation, size, and intensity. And we define those using the in-field data. And this allows for a more reliable analysis. As I said, the DFN represents the statistical representation of that rock mass. And it also allows for multiple realizations to be generated and to quantify the likelihood of events occurring. This can be a useful comparison for those of you who may be more familiar with conventional kinematics, for example. So, conventional analysis and a conventional approach is more conservative in that the fracture occurrence is ubiquitous. So, the fractures are generated everywhere and the maximum possible block size is produced. But they have a non geological orientation and they don't capture geological complexity. Whereas with the DFN, like I said, it's defined using the statistical definition of the fracture network, so that size, orientation, and intensity. And as a result, it does capture that geological complexity. And it not only is able to assess what could fail, but how likely different failures are to occur. So that probability of occurrence as well. So what are the inputs to this model? How can we generate it? Well, all modern data acquisition methods can be used to generate a DFN. So in order to define those three parameters that I've mentioned, for orientation, we tend to use mapping or borehole logging. Intensity can be defined using televiewer logs or photogrammetry, and size can be defined using things like the fault model, mapping, and photogrammetry as well. So once we have those three parameters defined, those are our inputs to the model to generate the DFN. And I'll just go through the three of those now. So orientation, we usually visualize orientation of fractures using these stereo nets that you can see on the right-hand side. And we can describe these orientations in two ways. The first is using a Fisher distribution, which is great when you have a very clear set or clear trend. We then can define a Fisher value which measures how closely those poles are to that mean of the set. Bootstrapping, on the other hand, is great when you don't have a clear trend or a clear set. It's great for sparse data and it takes into account the poles equally. So once you've described or defined your orientation, that's the input into the DFN. Moving on to fracture size. Um, we don't actually measure fracture size. We measure the trace length of fractures, and this is just as a result of the how we collect the data. So, for example, in underground mapping, we're constrained to the drift wall, for example, and therefore the trace lengths of structures tend to be less than 10 meters, for example, but highly abundant, as you can see in that picture in the top of the site photogrammetry. And if you plot those, they tend to be a normal log trend. However, if you consider these the trace lengths in relation to their count in area and you normalize them, you will see them aligned to this power law trend. And this is why we use a power law interpretation. So this power law trend is the red line there, and it allows us to describe or visualize trace lengths at different scales. So that underground mapping, like I said, up until pit wall scale major structures, which are thousands of meters in trace length, but not as abundant. And if you normalize them against their counting area, they'll align to a common power law trend, and this then describes a single size distribution of multiple structures at different scales. And that slope is then our defined input to the DFN. Moving on to intensity, we use the PIJ system, which looks at dimension of samples against the dimension of measurement. And the most commonly used intensity is P32, which is the area of fractures per unit volume. And while this can't be directly measured, it can be derived from other measurements, including P10, which is the number of fractures per unit length and is very commonly measured during borehole logging. So we convert that to P32 using the Chiles et al. 2008 correction, and that intensity is our defined parameter for the DFN model. So once we have that intensity, that P32 defined, we like to look at spatial relationships in order to constrain the fracture generation. So this allows for another layer of realism of how the fracture network is observed in situ to be added to the model. So we can look at things like distance from the ore, which is the picture in the bottom left-hand side, which shows fracture intensity increasing with proximity to the ore. Or we can also see the fracture intensity increase with proximity to structural model faults. And we can also look at things like elevation. So these spatial correlations and these spatial relationships also allow for inference of observed trends to areas with no data control or where data hasn't been collected. So finally, some application examples. For this, it was an underground mine which was experiencing some surface subsidence. The mine was built along this east-west trending fault, which was hosting the ore. So as the ore was being extracted underground, the surface was subsiding at the top. So with the progression of this subsidence, as mining was going to continue, there was a requirement for a more accurate prediction of the subsidence. So we defined a DFN, we defined that in situ fracture network of the hanging wall using size, orientation, and intensity from field data. And as a result, this is the DFN at the bottom. This is now an input to any future numerical subsidence simulations and will hold a better description of the hanging wall and those discrete fractures controlling or influencing that subsidence. The second example is in relation to geological complexity. So we have two lithologies here, limestone and a dike, and some faults running through them. And as a result of the structurally and geologically complex part of the site, there was a wedge instability, which you can see in the photograph. Conventional kinematics would have to model these two lithologies separately, whereas a DFN can consider them simultaneously and evaluate how they interact with one another. Furthermore, if you use a DFN 3D probability of failure approach, it was shown to reproduce that failing block, as you'll see in the photo in the bottom here, which is very similar to the instability zone. So this reproduction of the unstable zone provides confidence that the fracture network and the strength inputs are appropriate and that it can be used for any predictive modeling, which is the ultimate goal. So some final thoughts for you all. Modern data acquisition methods like televiewer, like mapping, like photogrammetry give us the data that we need to generate a DFN. DFN modeling gives structures realistic properties at multiple scales, and with realism comes greater reliability in predictions. DFN modeling allows simultaneous evaluation of multiple rock masses, and this provides more accurate stability analyses. And finally, DFN models are living models which can be updated throughout the mine life with evolving mine planning, with the ultimate goal to reduce structural uncertainty to allow greater reliability in our predictions and decision making in mine optimization. So thank you very much, and thank you to my colleagues at WSP, Kira and Steve, for their contributions to the presentation.
Brilliant. Thank you so, so much, Cara. As always, an absolutely phenomenal talk. Round of applause to yourself. So I think something that's really interesting. So we started off today with Freudis, who's talking about the decision making and risk is a social process. But then what you've just shown us here is when you then go into that very technical world where we really can embrace, laws of physics, etc. We can put numbers on these things, but they're still numbers that come with a range of certainty or confidence. When you're trying to explain to somebody who is not an expert in geotech, etc., what are some tricks that you use to explain to them just how certain you are about how a rock might fracture?
Yeah, it's a really difficult one. Like you could go to the very start of just the data alone, and you're going to have uncertainties in relation to maybe how that was collected, or during QA QC processes when we do quality assurance, quality control, it could turn out that, you know, the logger didn't interpret things as someone else would. There's always subjectivity in geology, and I'm sure we could all have a conversation about that in itself. Um, I suppose with something like this, we are very clear in how we are interpreting it to use in the DFN. So considering those uncertainties from the data alone into how we then define orientation, size, and intensity, we take those things and we state them very clearly to whether it's the client or the mine site. Um, And that's why having various forms of data collection is really, really useful for things like if we're looking at orientation, something that sets or an orientation that we see at the surface could be very different to what we're seeing in underground mapping, for example. And how we consider that is a conversation from my experience with the client. What are they seeing on site? Is this realistic? Is this as observed? Um, and then we can generate the model as we see fit going forward. Maybe put in all the orientation sets that we see. Maybe try it with two or one, and it creates more reliability in those future models of that fracture network.
And with this, Cara, have you ever been surprised in terms of, you've done all the modeling and then somebody actually digs a hole in the ground and you go, oh, that wasn't what we were expecting? Or what does that kind of feedback loop look like?
I can't say I've had the full project life cycle of doing the DFN and then them going away and actually seeing it, but yeah, it would be great to have that direct comparison of the DFN versus in real. But that's why we do calibration. So we have
Mhm.
unstable zones or we have those spatial correlations. So we look to calibrate the DFN with those things in order to have confidence that what we've generated is accurate to what is there in real life and then can be used for anything further.
So one final question, and this goes back to one of your first slides where you showed lots of great pictures of you out in the field, high vis, etc. What got you interested in this space? So why did you end up in this job?
Oh, so geologist by background, but yeah, I have to say I kind of fell into the mining world, which was the best thing that happened in terms of structural geology has always been very close to my heart in terms of I like the practical approach to it. Um, Modeling is very new to me and how we can apply things that are numbers into something that's a bit more theoretical or generated and is not real. I can't hold the core. I can't see it for real. Um and this in WSP we have some people that are experts in the DFN field and I've just been very lucky to be able to work with them and under them to learn how to do this aspect of it. But yeah, I think as a geologist working with other geologists and other engineers and various different disciplines in I think that's the beauty of mining that we have so many different perspectives um, to allow us to do something much bigger than my DFN model. It feeds into such a much bigger picture.
Yeah, and I love it as well. I mean, like the kind of the scope of diversity there. I mean, we've just described like different types of people that have geo on the front of their
Yeah.
discipline, let alone, going back to what Freudis was describing, where you've got like the entire diversity of the global population. It's really
Yeah.
interesting, isn't it, when people think, oh, well, I'm in a multidisciplinary team and I've got a geophysicist and a geotechnical expert and a geochemist. I think everybody else looks at that and goes, that is not diverse. Yeah, we might think, but it is.
Oh, like I wouldn't claim to be able to do anything that my colleagues in geochemistry do at all. So we are. It's incredible.
Brilliant. So with that, a massive round of applause. Thank you so, so much, Cara. As always, brilliant. Thank you
Thank you
very
so
much.
much.
Brilliant.